Hey everybody, this is a go over for Module 5, and in this video we're going to look at the Module 5 knowledge check as well as the Module 5 charge and electric field assignment. Then I'll have a second video with the Module 5 project. Okay, so let's start with the knowledge check. Okay, this is a play pause it. It's not letting me do. Okay, I have to watch it. There we go. Alright, so on these you see the little dots. These are where the specific questions are. So if you actually want to read the question ahead of listening to the information, you can. So that you know how to answer the question better. From Coulomb's law, if the magnitude of a charge doubles, the force it exerts on another charge is 4 times larger. I don't see anything here with 4 times distance, or the charge here times charge and the radius. So if the radius increases, it would. Electrons can be positively or negatively charged. Electrons are negatively charged. Coulomb's law tells us the force of one point charge on another. The force of one point charge on another. In the SI system, the unit of charge is volt. Okay, charge is measured in coulombs. So the correct answer is Coulomb's law tells us the force of one point charge on another. Okay. Electric field. Electric field lines originate on negative charges and terminate on positive charges. Kind of depends on who you ask. The SI unit of electric field is Coulomb. If the electric lines cross, the electric field at that point has 2 directions. If electric field lines cross, the electric field at that point has 2 directions. If the magnitude of the charge doubles the electric field, it creates doubles as well. I'm not saying, well, yeah, they probably already covered that one. So this one is correct. If the magnitude of the charge doubles the electric field, it creates doubles as well. Yeah, electric potential. Equipotential lines show the direction of the electric potential at any point. Negative charges are forced from regions of lower potential to regions of higher potential. In the SI system, the potential difference between 2 points is expressed in newtons per coulomb. In regions where the equipotential lines are close together, the electric field is relatively weak. Okay, so negative charges are forced from regions of lower potential to regions of higher potential. And And now we'll go look at the okay, so now that we've completed that, make sure you've walked through each of these and then come down and start charge and electric field. Okay, for the first question, you have to type in your name and walk through the little video series here. In the video, the students created two charged tapes, a pointy tape and a square tape. The pointy tape is first placed on top of the square tape, and the two were pulled apart. After pulling them apart, the students observed the behavior of the tapes when they were brought near each other, but not touching each other. How did the pointy tapes behave when brought near each other, and what does this demonstrate about their charges? Okay, the two tapes were prepared in such a way that the square tape and the pointy tape had opposite signs of charge. Like sign charges repel and opposite sign charges attract. The fact that the two square tapes repel show they have the same signs of charge, and the same is true for two pointy tapes. The square and pointy tapes are attracted to each other because they have opposite signs. Note, however, the attraction is not always sufficient evidence to show both objects have a net charge. Charged objects can attract neutral objects due to polarization effects in the neutral object. Okay, since the two have opposite signs, if you have two of the same, they'll repel because they have the same type of charge. And if you have you bring two squares to each other again, they'll repel because they have the same charge. And if you have a square and a pointy tape together, they attract and they have opposite charges because opposites attract. Two charged particles are a distance of 1.92 meters from each other. One of the particles has a charge of 8.08 nanocoulombs, and the other has a charge of 4.58 nanocoulombs. What's the magnitude of N of the electric force that one particle exerts on the other? So the force is measured in newtons. Is the force attractive or repulsive? Okay, so we look at Coulomb's law, and F equals KE times Q1 times Q2 divided by the radius squared. All right, so in this case, we were given Q1 and Q2, 808 nanos negative 9, 4.58 nano, again, negative 9, and then the distance from each other squared, 1.92 squared. And if we need to look at that on the calculator, that would be, I do this part first, and then multiply it times the KE. And we'd have 8.08 with an exponent of negative 9 times 4.58 with an exponent of negative 9. Okay, and I'm going to get an answer for that. and divide that by 1.92 squared and get my answer for that. And then I'm going to multiply that by the KE of 8.99 with an exponent of 9. And we have 9.02 times 10 to the negative 8. And since we have to enter an exponent here, this is how we'll enter the exponent, 9.02 e negative 0.8. And the forces are repulsive. Okay, here we're looking at the same type of situation. We're given two spheres separated by a certain distance. One has 5 times 10 to the 12 electrons are removed from one sphere and placed on the other. Determine the magnitude of the Coulomb force on one of the spheres, treating the spheres as point charges. Okay, each sphere is initially uncharged. When we move n equals 5 times 10 to the 12th electrons from one sphere, leaves it with a net positive charge of, and we can calculate it using E and the force. E is 1.6 times 10 to the negative 19th. And our force was given at 5 times 10 to the 12th. We multiply those two together and we get 8.01 times 10 to the negative 7th. So we look at entering this exponent the same way we did in the last problem. But that's not our final answer. That's the charge that's created. We can then use that to solve for the final charge. Okay, so we use KE times Q1 times Q2. Q1 times Q2 is the value we calculated up here. That's our Q. And our distance was given at 3.3. We have to square that. So this number divided by this number squared, and then times this number. Okay, in a radiation therapy device, an electron is in the presence of a uniform electric field with a magnitude of 330 newtons per coulomb. What's the magnitude of the acceleration of the electron in meters per second? How fast is it going? It's the magnitude of the acceleration. The electron is initially at rest. What's its speed in meters per second after 1.15 times 10 to the negative 8 seconds? Okay, so let's look at the magnitude of the force on the electron is F equals Q times E, which is equal to little e times big E. The acceleration can then be found as F over ME, or little e times big E divided by ME. Okay, so we have our little e is 1.6 times 10 to the negative 19th times the 330 newtons per coulomb that was given, divided by ME, which is 9.11 times 10 to the negative 31st. And that gives you your acceleration. You can then use the acceleration to find the speed, the acceleration times the time. So we take the acceleration we find here and multiply that times the time period that was given. Okay, determine the electric field strength at a point 1 centimeter to the left of the middle charge shown in the figure below. Enter the magnitude of the electric field only in newtons per Coulomb. All right, taking to the right as positive, the resultant electric field at point P, which is here. So if we have E2, E1, and E3 at point P, right is adding, so we add E1 plus E2, and to the left is subtracting, so we subtract E2. And then we can find E1 with K times KE times Q1 divided by R1 squared. This part should look familiar. We just have to do it 3 times and add these two together and subtract this one. Okay. And then multiply, this is the KE, so we find Q1 over R1 for each of these, and then multiply it times KE. This makes ER, or the resulting vector, positive or to the right, 2.00 times 10 to the 7th. And if the charge of negative 6.41 microcoulombs is placed at this point, what are the magnitude and directions of the force on it? So the force is equal to Q times E resultant, our vector up here that we determined, 2 times 10 to the 7th times Q, that was given as, the charge was given as negative 6.41 times 10 to the negative 6 for micro. So that gave me a negative 128 newtons, so that would be to the left. So the resultant vector is actually in this direction, or yeah, the force is in that direction. Okay, here we're looking at an electric field of magnitude 5.25 times 10 to the negative, not negative, 10 to the 5th newtons per Coulomb. Points due west at a certain location. Find the magnitude and direction of the force on a negative 7.3 micro Coulomb charge at this point. So we just multiply the two together. Since you're taking the absolute value of this, it negates the negative sign, and we end up with 3.83 newtons. Since it's positive, that means it's due east. And below we see a small charge bead with a charge of 39.0 Newton coulombs, nano coulombs. That moves a distance of 0.193 meters from point A to point B in the presence of a uniform electric field. Now this is actually fun, moving a ball from one point to another. I have a friend who's actually working on jet propulsion that involves some similar physics. It's kind of fun, actually. So what's the magnitude and the direction of the electric force on the bead? And then we want to know what is the work in joules done on the bead by the electric force as it moves from A to B. what's the charge and potential energy as it moves from A to B, and what's the potential difference in voltage between A and B. Okay, so the force is given with Q times E. So we take the 39 nanocoulombs, 39 times 10 to the 9th, times E, which was given at 290 newtons per coulomb. And that gives us our force. Since it's positive, the force is in the same direction as the electric field, to the right. The work can be found from the force times the distance times cosine of the angle. And the angle between the force and the displacement. In this case, both are in the same direction, so the angle is 0, and the cosine of theta equals 1. Okay, so we multiply the force times the distance that was given 0.193. And that gives us the amount of work done, which is 2.18 microjoules. The charge in the electrical potential energy of the system is defined to be the negative of the work done by the electrical force. And that's the equation way of saying that. So we're looking at negative the work here. The charge and electric potential is related to the charge and potential energy. The change in voltage is equal to the change in potential energy divided by the charge. The change in voltage is VB minus VA. The change in potential energy is PEB minus PEA. And so if we take VB minus VA, it should be equal to 2.18, which was the work done. That's potential energy divided by the charge, which was 39 nanocoulombs. And we get negative 56 volts. The negative sign is consistent with the fact that the electric field and the path from A to B are in the same direction. Cathode ray tubes used in old-style televisions have been replaced by modern LCD and LED screens. Part of the CRT included a set of accelerating plates separated by a distance of about 1.58 centimeters. If the potential difference across the plates was 28 kilovolts, find the magnitude of the electric field in volts per meter in the range between the plates. Well, we'd solve for the electrical field magnitude using the relationship between the potential difference and the constant electric field. Okay, so the change in voltage is equal to the negative of the electric field by the change in the difference of potential. Okay, so to solve for the electric field, we take the change in voltage divided by the change in potential difference. The change in voltage was given at 28 kilovolts, 10 to the third for K. And the distance was given as 1.58 centimeters, -2 for cent. Volts per meter and newtons per coulomb are equivalent. All right. Hope that helps with Module 5 problems. If you have any questions, please let me know.